And so we're very glad to have Jiří Adámek today talking about C-varieties of ordered quantitative algebras, which is joint work with Jiří. So you can start when you're ready, Jiří.
Yes. So, first of all, I want to say this is the first time in my life I'm using this technology based on a camera that makes it possible that I write live. And if things get unreadable or whatever, John, it's your task because you're unmuted to give me a hint. So, first of all, let me start with explaining my title. What are C-varieties of ordered and quantitative algebras? So ordered algebras are algebras enriched over the category of posets. So you have a poset with operations that are monotone and homomorphisms that are monotone. And if we speak about classical varieties, so without any extra structure, then a variety is simply a class of algebras of a given signature, which is presented by some equations between terms. Now, in case of ordered algebras, the only difference is that you have inequations between terms. So an algebra satisfies an inequation if whenever you compute the two terms, you get an actual inequality in your algebra. However, unlike the talk a couple of weeks ago, Jiří Rosický gave, my signatures will always, throughout my whole talk, the classical ones, which means a bunch of equations, each with a natural number as arity given. What are quantitative algebras? That's the usual computer science description for things where you have a metric on it. So we now speak about algebras enriched over the category of metric spaces. When I say metric space, I again don't mean any Liouville generalization, just the classical thing with a single exception, namely distance infinity is allowed. This exception makes it namely that when you take as morphisms, non-expanding maps, so maps that never increase distance, then you'll get an Aleph-1 presentable category and otherwise you wouldn't. Now, what is C-varieties? This has to do with a rather new and, in my opinion, excellent idea. I'll come to it when I come to quantitative algebras, that you also put some structure on the variables that you are using. So come back again to ordered algebras. An equation is a pair of terms. And these terms have some variables in them. And if you speak about C-varieties, you also put some inequalities on these variables, and that this is a good idea, I'll try to persuade you. And the word C, also the letter C here, is actually a variable cardinal number, which says you have less than C such possible restrictions on your variables. So for example, when C is equal to 1, you have less than 1, this is none. So that's a classical case. And the most interesting or natural one will be C is Aleph 0, where you just put finitely many on them. I'll come to that later. So, before I plunge into ordered algebras and in the second part of my talk to quantitative algebras, let me start with classical case because the comparison will have a certain explanation in it. So,
Jiří, can I ask a question? Actually, just did you have a light on a while ago?
No.
Okay, so there is no. It's okay. It looks fine. It looks fine.
Is it better?
I think it's quite similar, actually. I think it was okay the way it was. I think it was okay.
So is it hard to read?
I think it's quite similar. If other people have an opinion which was better, I would say something. I think that's okay. I think it's okay. I think it's readable, yeah.
So classical varieties. There you have a signature and you form the category of algebras over that signature in the category of sets. So this is not the usual notation for sigma algebras, but I want to distinguish between algebras in sets, in posets, and in metric spaces. And then you form the free algebra. Aha, you don't have only that. You typically have a standard set of countably many variables. This is an unimportant thing. You can also work with arbitrary variables, but that's what algebraists very often do. So you have a countably infinite set of variables and form the free algebra on that countable set, and that's the algebra of terms in the usual sense. And then a pair of terms is typically written in this form, but it's nothing else than a pair in this set. And this is simply a classical equation which an algebra satisfies if and only if for every interpretation of the variables, if you look at the free homomorphism, free extension to a homomorphism, then the value of T and S is the same. Now, in the classical dissertation of Bill Lowier that really changed the view of categories at algebra, there is also one result that is not so well known and which is really beautiful. And that says, so take these varieties. So by a variety, I mean simply a full subcategory of this category of sigma algebras over set presented by equations. And you can characterize these varieties as categories. So what is that Lowier did was to say a category K is equivalent to a variety if and only if. And now he had a couple of conditions. One was then you have to have finite limits and co-equalizers. So this is very standard. The other one is your equivalence relations are effective. So every equivalence relation is a kernel pair. And the third one is you have a very special generator, namely a regular generator, which is finitely presentable and regularly projective. So one of the nice developments about this theorem is due to Pedicchio and Wood. Who said you can get rid of the only condition in this theorem that's somehow non-standard, and actually the one condition that when we come to ordered algebras causes difficulties. I'll explain what I mean by that. If instead of regular projective, so maybe I should remind you what these three things are. So a regular generator is an object G, which has copowers, and every object, if you take an object X, and you take the copower of G, the standard copower by all morphisms that go from the generator to X, you will get a morphism and the canonical morphism. And being a regular generator means this morphism is a regular epimorphism. Finitely presentable means that the Hom functor, which in this case, because we are in sets, goes into set, preserves filtered colimits. And the last condition is that it preserves regular epimorphisms. So what Pedicchio and Wood did was to say, if you want to get rid of condition 2, you have to be a bit more strict about projectivity. And this means what they called effective projective, which means that this not only preserves regular epimorphisms, the Hom functor preserves co-equalizers of reflective pairs. So let me remind you, what does it mean that a pair of morphisms is reflective? It means that they are split epimorphisms with a joint splitting. And why are reflective pairs important? Because in varieties, co-equalizers are of course not preserved by the not formed on the level of sets, not preserved by the forgetful functor, but reflective co-equalizers are. Okay, with this background, let me begin with ordered algebras. So I am still not at C varieties, but just as at so-called, so to say, classical varieties. So here I am now speaking about things which look as follows. You have still your signature is a bunch of equations with natural numbers as arities. And this category has as objects posets with monotone operations and as morphisms, homomorphisms preserving these operations. And a typical a variety. Now you again form this algebra of terms. If you allow me to consider every set in the world as a poset, then there is absolutely no difference from what I said before. So you don't put any, V is just a set of variables, and therefore discrete poset. You form the discrete poset of terms, and this is the free sigma algebra on V. And now the varieties are those classes where you take a pair of terms and say the algebra has to satisfy such an inequality in equation in the obvious sense. And a variety is then a full subcategory of algebras satisfying a given collection of inequations. Now, this has to do with monads on POS in precisely the same sense in which the classical story has to do with monads on sets. So remember, finitary monads, so those monads preserving filtered colimits, are nothing else than varieties in the strongest sense. Namely, you can form the category of all varieties over set and all functors between them preserving underlying sets. And an equivalent, a dually equivalent category is a category of finitary monads over sets and monad morphisms. Precisely the same thing happens by monads on sets, which are strongly finitary. So what does it mean? Two things. They preserve filtered colimits, and they preserve co-inserters of reflexive pairs. So before, I was speaking about these co-equalizers of reflexive pairs, those that are in algebra formed on the level of set. Now I speak about co-inserters of reflexive pairs, which are those co-inserters. Let me remind you that if you have a parallel pair of morphisms, a co-inserter C is a universal morphism with a property that F1 followed by C is smaller than F2 followed by F0, sorry, F1 followed by C. And now we additionally have this joint splitting of this pair. By the way, I told you a characterization of what strong definitory functors are, not their definition, that I don't need and therefore won't mention. In John Burke's thesis, this equivalence is proved. So now one is allowed to say strong definitory means these two things. Okay, so these are the monads on cos. And now comes the theorem. And this actually stems from a paper by Kurz and Fellebill about 6 years ago, who proved that varieties in over cos are precisely in exactly the same sense as in, I said, in the classical sense, the strong definitory monads over cos. There is one catch in this paper that, in my opinion, it's unreadable. I'll tell you why. Because they did not work with this wonderful improvement by Pedicure and Wood. So these crossed rest things don't appear in their paper. And therefore they spent pages and pages explaining what this effectivity of equivalence relations is in varieties. I am not a person who easily works with enriched categories, and for those who do, I don't doubt that it's a wonderful paper that brings something new. I tried to read it many times and I didn't succeed. So that's the bad news. And the good news is that together with Jiří Adámek and his previous PhD student, Matěj Dostal, we now proved exactly the same theorem, avoiding completely the catch about effective equivalence relations. And an even better news is that Jiří Rosický then showed us how to prove it more generally and more, well, I don't know, elegantly is hard to decide. Well, I love our proof, but there is no doubt that his system of using operations of arities xy, as he explained in his talk a couple of weeks ago, works effectively. So his proof is shorter and moreover more general. Anyways, you don't need to go through effective equivalence relations when you want to speak about varieties of ordered algebras. And now there is one reason why you should be interested in C varieties of ordered algebras. And the reason is that there are no fascinating examples. So the question is, what are examples of varieties of ordered algebras? Well, of course, there are classical examples like ordered groups. or ordered monoids. You can add to ordered monoids. So my next examples is you take your neutral element and you insist that this is the least element of your poset. But somehow I would have loved to have an example of a new type of variety, which is not taken from the category of sets and then added some order. And such doesn't exist. So I mentioned this paper of joint paper with Vellebil and Dostal, and one of the theorems in that paper is for every ordered variety, its monad is a lifting. So you have a monad now, T on pos, is a lifting of a monad on set. What does lifting mean? Well, you have your underlying functor, and you have for the other monad its underlying functor. And when you take the forgetful functors, this commutes or commutes up to natural isomorphism, both give the same result. And also, of course, the unit and the multiplication are lifted from the category of sets. So in a sense, these three examples are typical for ordered varieties as such. And this brings me to C-varieties of ordered algebras.
Jiří, can I ask you a question?
Absolutely.
In the previous theorem, could you give us at least the intuition of why this is true for posets and what kind of categories we can expect to have in that theorem?
Yeah, I'm happy to. The trick is that one knows how to construct a free algebra. So you now have your given variety in this category. And there is a concrete description of free objects. So actually, I'm now speaking about the left adjoint to the forgetful functor V. So how does one construct a free algebra on a given poset? Well, the construction is rather standard, and in that sense, you are right. What you indicate, Ivan, that it might be a general thing. Well, you simply take all algebras of your variety and all homomorphisms that are surjective, and then you take the product of all these and you factorize this into a epimonofactorization. So the main thing is you have this factorization system, and that is the E part are simply surjective homomorphisms, and the M part are those monomorphisms that are carried by order embeddings in POS. And you use it in a very standard manner to get your free algebra. And now forget that you are in posets and do the same thing in set. And because again, epis are just the surjective things, you will get the results. So that's the idea of the proof. Is it?
Thank you very much. Yes, yes. Thank you.
Very nice question. Thank you. Okay, so C-varieties of ordered algebras.
Sorry, can I ask one question as well, actually, about that?
I am happy. By
just back on the same page before. You're not saying though. I mean, there can be more than one lifting to pose.
Look at this example. Of course, both of these are liftings of monoids.
Right, okay, yeah. That's right.
Yeah.
Thanks.
You're welcome. As I say, questions are very, very much appreciated. So I already warned you that the C is a parameter. And since we have finitary signature, there are only two reasonable choices, namely the classical thing, which was my previous slide, no further restrictions on variables. And the other one is if you choose Aleph 0, then you are allowed to give finitely many restrictions on the variables. So before I define what a C variety is, here is an example. What example was if x is smaller than y, then x plus y is equal to y plus x. So this would be a variety where you have an operation plus. This is not required to be commutative, but among those elements that are comparable, it is commutative. So in general, a C variety is given by a C inequation, which has the following form. You take, well, I'm now speaking about not C inequation, but Aleph 0 inequation. You take finitely many conditions on variables, and you derive, so this is a derive symbol, that two terms are, so here I should have said not implication, because implication has a meaning in algebra, but derive. From the fact that x is smaller than y, you derive the commutativity. And in general, you have an inequality between two terms. So, as I say, my motivation for it stems from computer science, where it was used in the category of metric spaces. And it's about 2 years ago when there was still possibility to see another country that I visited Jiří Rosický, and we said to ourselves, well, this is an interesting concept. Why not investigate algebras that do this? And nowadays I have another motivation that namely in this way you get classes. For example, here you have immediately one that are not liftings from sets. So you leave the universe of varieties in sets and their enrichment, and you get something really post-theoretical. So what are the varieties? What are the monads that express precisely, so what a C variety of ordered algebras is, I hope is clear. You form now a full subcategory of sigma pos given by a bunch of Aleph 0 inequations, in the sense that the algebra must satisfy each of them. And each such subcategory is monadic. And these monads are not strongly finitary, of course not, but they are, of course, finitary and preserve epimorphisms. Maybe I should have started by, when I was in the classical case, I said, varieties classically are just finitary monads. Now, yeah, but in sets, they automatically preserve epimorphisms. They are automatically preserve split co-equalizers. So these types of monads really naturally generalize the result. And what is the result? That's from the paper with theorem. Again.
Jirka, just a question. Present epimorphism or surjections?
The same.
in both sense.
Sorry. So if we have, I think it was epimorphisms. I sent you the proof.
Yes.
Good.
And I also have a small question.
I know the answer. It's both. In these categories, and that's important. In the C varieties, the epimorphisms, no, it can't be true. That's not even true in varieties. So now you really got me, Jirka. Maybe I'm wrong. So, sorry. Now I'll tell you a theorem I am sure that it's true. Namely, this one. So on the one hand, you have those homomorphisms in your sigma pos that are carried by certain monotone maps. And on the other hand, you have the same thing in your C variety. And the certainly true theorem says that a monad, so that that Aleph zero varieties in sigma pos correspond in the strong sense, as I said before, as equivalent categories to precisely those finitary monads that preserve surjective morphisms.
Only one clarification. Do you mean enriched monad or monad?
Sorry, that was my mistake. So let me come back to the previous result where I said strongly finitary. And in that case, it's a part of the definition. So strongly finitary monad is an enriched monad, which means one preserving one which is monotone on home sets, which is a left-hand extension of something. And as I said in John Bulk's thesis, it's proved that it's the same thing as a enriched finitary monad preserving reflexive co-inserters, and I just forgot the word enriched.
Thank you.
No, I thank you. So these are precisely the enriched finitary and preserving surjective morphisms. Okay, so what is the overall situations with finitary monads on POS? And now I will not make the same mistake again, and I will divide my page into enriched and unenriched. So those 2 years ago when I visited Jirka, I said the classical finitary monad variety thing in Z. What does one know about posets? And we started looking at literature and couldn't believe our eyes. There wasn't a result. And now I think we have a rather good overview of what's happening. So on the one hand, the least class, so you have on the here the thing about C varieties. And the other thing is about monads. The smallest class are the classical ones. So these are the those given by inequations. And we know they are precisely the strongly finitary monads. Then comes the class of all extensions, or liftings, sorry, liftings from set, I mean liftings of finitary monad from set. And here you can also speak about liftings. It's very easy to define what is a lifting of a variety. Essentially, it means you just add to your given algebras order in such a way that the free algebras are formed in the same way. The next result is preserving about those which preserve surjective morphisms. And these are the Aleph 0 varieties. And then comes the question, what type of algebras has to do with all enriched finitary monads on posets? And this is outside of my talk. That's why I am not making a box here, but it's inside of a joint paper with Milius, Ford, Schroeder, and myself. Where we work no longer with classical signatures, but with enriched signatures, and that's what I want to not use in my talk. Let me just say is the same story I already mentioned once, namely, we presented this result, we were proud of the way how we proved it, but Jiří Rosický put it into his machinery and has a proof that's more general and shorter, and that's how the situation is. So this looks like a rather complete, what would you so wish to know about finitary monads over pos? Well, of course, you would know to wish how important it is to be enriched. And the answer is bloody important, because what you get is again a complete, so again, I will write it in the red color in the sense it's outside of the signatures that I am using, but all monads, all finitary monads over pos have to do with algebras that have order on their underlying set. Homomorphisms morphisms are order preserving homomorphisms, but operations are not monotone. So although I put it in such negative terms, it's actually a positive theorem proved in this paper with Milius, Ford, Schroeder, that the category of all finitary monads over pos is dually equivalent to the category of varieties in this sense, which in my categorical opinion says this is a very unnatural realm, and it's good to simply put this as an advertisement for enriched category theory. So how much time do I still have?
Yeah, before you remove this, can I ask just on the left column, I'm confused. So you have up there C varieties, and I understand C can be 1 or Aleph 0, and then you have Aleph 0 varieties.
Yeah, thank you. Here is C Aleph 0, and here is C equal 1.
Ah, okay.
Yeah. no condition on the variables.
Thank you. Okay.
Finitely many conditions on variables. And the whole thing is, of course, completely generalizable to lambda array. So you give me a regular lambda, and then I can speak about lambda array operations and lambda array varieties. And if you take C equal lambda, which means you are allowed to put less than lambda in equations on your variables, you get precisely the lambda accessible monads preserving surjective morphisms.
Okay.
Thanks for the question. So, metric spaces. There is about 4 years ago.
By the way, sorry, I forgot to say you have 15 or 20 minutes, up to you.
Wonderful,
is that...
wonderful. The name C-variety stems from a paper by 3 very well-known computer scientists, Mardare, Panangaden, and Plotkin, and is the same idea as I said before. So for example, this category I already explained. Met means metric spaces with possible distance infinity. Morphisms are non-expanding maps. And when I say sigma met for a signature, then this means the algebras carry a metric, and therefore the name quantitative used in computer science, and homomorphic operations are non-expansive and homomorphisms are non-expansive. This time, however, I will take sigma aleph 1 accessible, that is, arities are not only finite, but also allowed to be aleph 0 itself. Why? Simply because this category is not locally finitely presentable. For those who don't know it, here is the reason. The reason is, take the following omega chain, namely 2 elements of distance 1, the next one is 2 elements of distance 1/2, and so on. What happens with this chain is that it does have a colimit, and the colimit is a singleton point. And this shows you that actually no non-empty metric space preserves omega colimits. I mean, the home of a metric space. Therefore, no non-empty metric space is finitely presentable. So we typically would now speak about everything that is aleph 1 accessible, so preserving not only preserving only countably directed colimits, and therefore my arities are now allowed to be also aleph 0, and the 3 interesting C's, I'll define what a C variety is in a minute, are now no longer only these 2 ones, but also the aleph 0 one. So what are my what is that I would call a C equation? In this case, you start with a countable set of variables. You form your, and now every set, again, the infinity distance has a great property that every set is also a metric space, namely the discrete space. All distances of different points are infinity. And so my set of varieties is again a metric space. I form the terms. Now, of course, terms are a bit longer than before because we have these aleph 0 array operations. And if I have two terms, then without any previous condition on the variables, I would write, so the three people here wrote their equations in the form T and S are terms, and epsilon is non-negative rational. And I think that everybody has a clear idea what this means. This means an algebra satisfies it if for every interpretation of variables in my algebra, when I look at the unique homomorphism, because this term algebra is again the free algebra on V, then the distance between the two terms as computed in my algebra is requested to have a distance at most epsilon. Okay, and what is the C equation? Here you have a typical restriction of, let's call it delta this time, not one but many, and from this set of equations of cardinality less than C, you derive your equation T epsilon S. So when does an algebra A satisfy it? When the same holds as before, under the condition that your F that you use satisfies the things that are prescribed in the first part of the equation. So given an interpretation of variables such that whenever there is this restriction in your algebra, it's satisfied, then also the conclusion of that inequation is satisfied. Now, I already said something unnice about a paper of Kurz and Felber, which is not very nice of me, is they can't defend themselves. It's much worse in the case of Mardare, Pangadin, and Plotkin, because they really do everything to dissuade you from reading the paper, because they start with arbitrary implications. So they pretend that they are not working with varieties, but with quasi-varieties. And it took Jiří and myself quite some time to read enough to understand, no, they are doing something really wonderful. They are making a really good compromise between classical varieties that would be given just by such things, and something that, in my opinion, is not very interesting, namely quasi-varieties. So, for example, quasi-varieties are typically not monadic, whereas, so now I'll cite the paper, Mardare, Palmgren, and Plotkin.
Jiří, would you be able to actually just move the page upwards and to the right slightly? I think it's been, just raise it. Yeah, perfect. And a little bit, push it a little bit up as well. Perfect, yeah.
Thank you. So, as I say, the paper is written very computer science oriented, plus this quasi-variety feature very much stressed, so that it took Jiří and myself quite some time to understand what's happening. And when we did, we rejoiced, because here is the theorem, which tells you that what these three gentlemen are doing is actually a very natural thing from the categorical point of view. So take sigma, a signature of arity, as I said, aleph 1, so operations of arities less than equal aleph 0. Then the aleph 1 varieties, which means you allow countably many conditions. In the previous slide here would be, you are allowed to have a countable list of conditions. They correspond in the strong sense as before to precisely the enriched monads. What is enriched now? That means your endofunctor is non-expanding on home sets. Of course, you don't expect that now comes finitary, rather it must be aleph 1 accessible. Monads preserving surjective morphisms. So the story is analogous to the story I said before. I presented a proof based on the techniques that were developed in the paper with Kurz and Dostal, and Jirka immediately showed a better proof using his XY operations. And therefore we are doubly sure that the theorem holds. And it somehow shows that this is a very natural concept. Why is it used in computer science? Because the important part of programming is with probabilistic methods. And there you typically use algebras which have a metric as a basis. Anyways, in the paper that I first cited, and then I said it's not so good, they also speak about aleph 0 varieties. And what they write there is simply mathematically not correct. And so the question is there anything that can be said in this context? And I suppose the answer is no. It's from a categorical point of view, you have a aleph 1 accessible, aleph 1 locally, aleph 1 presentable category. Why should you expect to have anything that has to do with finitely many conditions? But I have no idea. And now comes the interesting question. This is really something that Jiří and myself tried to think about. So I'll now put 2 question marks, and we don't know the answer yet. So that would be a fascinating thing to know, which aleph 1 accessible monads correspond to the case where you only allow your equations to have the type that occurs to one immediately. Okay, now I would very much like to come back to the beginning of my talk and work for a bit again with algebras enriched over concepts, namely abstract characterization. I have this abstract characterization for set enriched before. And the good news is we have an analogous situation in var. So the regular generator will be just different in the sense that instead of here having irregular epimorphisms, you will simply, so a regular epimorphism is a co-equalizer, and here you will have a co-inserter. This is unchanged, and here again, instead of this effective projective, you will work with co-inserters. So what is my claim? My claim is that a post-enriched category, so this is again a joint result in my work with Jiří Grosicki, a post-enriched category is equivalent to a variety, and now I mean C equals 1, so the classical variety, if and only if. First of all, it has reflective co-inserters. So the co-inserters of reflective pairs you can form. And secondly, it has a generator. I call a morphism subregular if it is a co-inserter of whatever pair. Just to imagine where we are in the category of posets, these are precisely the surjective morphisms, whereas regular epimorphisms are much more than just being surjective, of course. So it's a subregular generator, where before we generator G, before I said it has arbitrary coproducts, now I have to say more. Arbitrary tensors, where P is a poset, plus the condition that for every object X, this canonical MEP you have. So you take now not the set, but the poset of all morphisms from G to X, and you take the tensor with G, then you will get a subregular epimorphism. So it's a subregular generator, which is finitely presentable, no change from before, and which is not an effective projective, but a sub-effective projective. And that means, oh, I said there is no change from before. That's of course not true. Apology. I now, of course, when I say the home functor preserves filtered colimits, I mean the home functor that goes into pose. And the same here. So the home functor preserves reflective coinserters. The good news is the theorem looks exactly the same. The bad news is it seems to be much harder to prove. So we sweated quite a lot, and now we are working on ideas how to make the proof easier. Thank you. That was what I wanted to tell you.
All right. Well, thanks very much for a nice talk. And so we can have our usual sort of silent round of applause. And yeah, and so if anyone has any questions, they can go ahead and ask. Jiří?
Yeah, can I ask first a question on clarification on MET, on the category? So these are just ordinary metric spaces with the only exception that value infinity is permitted, right?
Absolutely.
Okay, all right. Just wanted to make sure. Now I do have a question on the ordered case.
Yes.
So when it comes to ordered algebraic structures, the first thing that comes to mind that people actually use is ordered vector spaces.
Okay.
But I think there the thing is more complicated because you have a positive cone. Right?
Yeah.
So you, in some sense, you have two underlying sets that are relevant. So I wonder, is anything of this covered by your theory, or do you have the hope that it can be extended to include ordered vector spaces?
Thanks for the question. I'll think about it. I have no idea.
We have a little bit in a paper with Lourdes for the Trankova proceeding. We have a little bit on this category in that paper, but
okay, I'll have a look.
It's a few years back, so I don't remember all the details myself.
I have the volume.
Okay.
So I have a question. These C equations, they kind of remind me of universal Horn sentences or Horn logic. So is there a connection?
Ooh, I have no idea, but I'll have a look. Universal ones?
Yeah, so these are sentences of the form, you know, just a conjunction of atomic formulas imply another conjunction of atomic formulas. I think there's actually some section on that in your book with Jiří Adámek, the locally presentable accessible categories book.
Well, thanks for the hint. I'll have a look.
Okay, thanks.
I have a couple of questions.
Yeah.
So the first one is about enrichment basis. I think I already said it to Jiří, so let's try again. Another enrichment base that I think might be interesting to study is pointed sets, especially for computer scientists, because this is a good model for partial functions, and they study partial operations that are not defined everywhere. So I think pointed sets with the smash product could be another place to look at.
Okay.
And then another question I had is about the definitary case in metric spaces.
Yes.
Did you think about monads, finitary monads preserving embeddings? Maybe this is more a question for Jiří Rosický, in connection with your paper on Banach spaces.
So this is an important case because you, as Jirka showed us, that no non-empty metric space is finitely presentable, but all finite metric spaces are finitely generated with respect to dialectical isometries. So you could use this technology, but for that you need that this monad preserves those. But this is not true in general. So maybe a way how to try to, you are right, a way how to try to approach these finite varieties is to look at monads preserving isometries. But you will not capture all varieties then, because that's not always true. So, but that's good hint, yes.
And then maybe last comment I wanted to make is connected to Mark Kamsma's comment, which is, so in the case of the classical Gabriel-Ulmer theory, we know that limit formulas can be used to describe varieties. Of course, they can be used to describe locally finitely presentable categories, so in particular also varieties. Do you have a notion of limit theory in the enriched case?
No, you don't. It's a good hint.
But you have finite sketch, yes? Their specifications are finite weighted limits.
That's definitely true, but
I know
this is
the whole, yes.
It's very categorical, that presentation. I was thinking about something more logical.
Yeah, well, I find it a good thing to have a look at. So we don't know anything, but something I would look at. Thanks.
Thank you. I'm done with my questions.
Any more? Any more questions? Well, if not, then let's thank Jiří again for a very nice talk. And that's it for today. So I'll just mention that next week we have Michael Ching, who it hasn't given me a title yet, but he'll be talking something about tangent infinity categories. So that's the plan. So don't know what time it will be exactly where he is. So hopefully he can wake up for it. And yeah, so that's all for today. Thanks to everyone for coming, and see you next time. We can stop recording.